Okay, let us move on with our coordination numbers. In the last class, we covered the low coordination numbers, 1 to 3. We saw that these coordination numbers are fairly rare. Then we have the intermediate coordination numbers, 4 to 6. So these are by far the most common coordination numbers. Now let us discuss high coordination numbers, which are again not so prominent, but still observed in nature and therefore deserve a discussion as well. So the first coordination number that I would like to discuss is the coordination number 7, so similar to the coordination number 5. No structure is clearly preferred. Actually, there are 3 structures that are observed about equally common. So the first one is the pentagonal bipyramid. An example for that would be the hepta fluorozirconate 3-. So in the pentagonal pyramid, as the name says, we have a pentagon in the pentagonal plane with 5 equatorial ligands, and well, that pentagon is then capped by 2 additional ligands, which are then the actual ligands. So the second shape associated with the coordination number is the so-called the capped trigonal prism. So an example for that is the heptafluorotantalate 2-. And you see the structure here. So you see that these 3 fluoroligands here, they make a prism. You see that this triangle here and that triangle here, they are actually eclipsed. Yeah? And then you have the 7th ligand capping the square, which is made of these 4 ligands belonging to the different triangular faces. So can you imagine why the 7th ligand is actually above one of the squares rather than one of the triangular faces? Can you unmute yourself?
Is there like less steric hindrance if it's above the square instead of the triangle?
Yeah, correct. So there's simply more space, right? Because the square is somewhat larger than these triangular faces here, and therefore the 7th ligand has less steric hindrance with these 4 ligands rather than with the 3 ligands that are part of the triangle. All right, so the third structure is the capped octahedron. So an example for this is the tribromo tetracarbonyl tungstate. And you see that in this structure, we have the 3 CO ligands on one face here, and the 3 bromo ligands here on an opposite face. Okay, and then the 7th CO ligand is being placed above the face that is made of the other 3 carbonyl ligands. So this is the third possible to realize the coordination number 7. So like for the coordination number 5, the ligands are not always, they are not all symmetrically equivalent. So for the pentagonal bipyramid, as we have previously seen, well, the axial ligands are different from the equatorial ones. Now for the capped trigonal prism, the seventh ligand above the square here would certainly be different from those ligands who are making the square here, as well as these two other ligands, which have a greater distance from the seventh ligand than the other four. And here in this structure, again, the seventh ligand would certainly be symmetrically different in comparison to the other six. And these three CO ligands are also symmetrically different from these three bromo ligands, because these three ligands are closer to the seventh ligand in comparison to the other three. All right, now let's go from the coordination number 7 to the coordination number 8. Okay, so the most simple shape that you could associate it with the coordination number 8 is actually the cube. You see here a model of the cube, but the cube is actually not known. Instead, a slightly different structure is preferred, and that's the square entaprism. And you see here the difference between the square entaprism and the cube. In a square entaprism, the two opposite squares are actually rotated by 45 degrees. Okay, so I made a little video how this interconversion works. So these videos actually consume a lot of bytes. Therefore, I could not upload this version of the PowerPoint slides into core sites. So you have this slide on a somewhat different version that does not contain these videos. So if you wanted to look up these videos again, please go to the respective YouTube video where you can see them again. So now here we start out from the cube, and then we just twist one square face by 45 degrees. Okay, and then we produce the square entaprism. So this structure here is now the same as this structure. Okay, then we have a third structure, which is actually related to the square entaprism. We can view it as a kind of a distorted square entaprism. It is a dodecahedron, so that means that we have 12 faces, and these 12 faces are 12 triangular faces. You see this here. So you see here, for instance, one triangle, and here another one. And there are, well, 10 other triangular faces in addition. So this structure is a little bit more complicated to understand, but one can understand it more easily when we see how the square entaprism can actually distort the form of dodecahedron. I've made a video about this as well, and this works the following way. Okay, so we distort the bottom square of our square entaprism. I see this here. And now we also distort the top one. Okay. And this creates, well, the triangular faces. And in order to see that, I'm placing here the respective faces of the triangles in addition. Okay. So now you see that this polyhedron here is actually exactly this polyhedron over there. All right. So examples for that dodecahedron here, which is not the Platonic solid, by the way, we have a significantly lower symmetry here, is, for instance, octacyano-molybdate 3-. An example for a square antiprism is, for instance, the tetraoxozirconate 4-. Okay, now let us go from the coordination number 8 to the coordination number 9. Now, one example for the coordination number 9 is the nona hydridorenate 2-, which is a tri-capped prism. You see here the rhenium in the center of the prism, and we have 6 hydridoligands here and 6 hydridoligands here that make the prism. See that this triangle here and that triangle here, they stand eclipsed relative to each other. And then we have 3 caps above the 3 squares here. So here the first hydrogen, which stands above this square, made of these 1, 2, 3, 4 hydrogens. Okay, then we have this hydrogen here, which stands above this square, made of these 4 hydrogens. Okay, and last but not least, we have this hydrogen here, which stands above the fourth square, which is actually this one here. Okay, now can also have other structures. So one example is, for instance, the capped square antiprism. Okay, an example for this would be the nona amine lanthanum 3+, and in this case we would have a similar structure as here, but these 2 triangular faces would not stand in an eclipsed fashion, but in a staggered fashion. So they would be rotated 90 degrees by 90 degrees to each other. So now you can think about, well, what do these structures or examples for these structures for high coordination numbers all have in common? When you see, they all tend to have large metal lines in the center. In this case, lanthanum and rhenium. And in the previous examples here, it was zirconium and molybdenum. And for the coordination number 7, we again tend to have larger metals in the center and relatively small ligands around. So in this case here, it's a hydrogen. And in this case here, we have amine ligands, and you can easily conclude from that for that reason, we will have relatively few examples of high coordination numbers in comparison to intermediate coordination numbers, just because there are not as many metals that are so large, and there are not that many ligands which are small enough to fit around these large metals. So the coordination number 9, by the way, is not the largest coordination number possible. So coordination numbers up to 16 have been observed, but they become increasingly rare, and we're not discussing all of them. So with this, we have finished now our chapter about the coordination numbers and the structures associated with them. We can now move over to the next chapter, which is about isomerism. So you know isomerism probably from organic chemistry, where it plays an important role, but it's also important for coordination chemistry. So there's an overlap between the isomerism in organic chemistry and the isomerism in coordination chemistry. So you will probably know some of the concepts that we're discussing in the following, but some forms of isomerism are also unique to coordination chemistry, and these forms of isomerism will be new to you. So generally, what defines isomerism? So when two or more compounds have identical empirical formulas, but different structures, then they are called isomers. So isomers, when you do element analysis, they always have the same empirical formulas, but if you analyze their structures, then they have different structures. So now, what kind of isomerisms do we know? And the two basic categories are, first of all, the constitutional isomerism, and secondly, the stereoisomerism. So what is the basic difference between these two? In the constitutional isomerism, we have bonds between different atoms. Okay, so the bonds are not between the same atoms. And in stereoisomerism, the bonds are between the same atoms, but the coordination sites are different. Okay, so the bonds are in different places. Okay, so they're the same atoms, but ligands are in different coordination sites, and the metal ligand bonds are in different positions, therefore. So let us first look at the constitutional isomers in constitutional isomerism. So what kinds of constitutional isomers do we know, and what are examples for them? So first of all, there is the hydrate isomerism. So this isomerism only occurs in solid state crystals, simply because it doesn't make sense to define hydrate isomerism in solution. So in hydrate isomerism, we have isomers in which one isomer has water molecules in form of isolated water molecules inside of the crystal, which are not directly bound to the metal, whereas in isomers to that, that respective water molecule is actually bound to the metal directly. So one example is here. So here we have an hexa, hexa aqua chromium 3+ cation with 3 chloro ions in the second coordination sphere. So a hydrate isomer to this compound exists, in which one of the 6 water molecules are moved out of the coordination sphere and is now just bound as, well, water molecule as part of the crystal structure, but it's not directly bonded to the chromium anymore. Of course, such a hydrate can only exist in solid state. It doesn't make sense to define a hydrate in solution, because let's say we dissolve this here. Well, the water molecule would become part of the solvent, and when it's part of the solvent, it's not making sense to say it still belongs to the compound. So there can only be 2 isomers. There can be more than 2 isomers. So for this system here, there's actually a third one. So we can move another water molecule from the first coordination sphere into the second coordination sphere. Okay, and then we move another chloro ligand from the second coordination sphere to the first coordination sphere. In this case, not necessarily would have to do this. So this a chloro ligand could also stay in the second coordination sphere, but in this case, nature doesn't doesn't do this, if it stayed in the second coordination sphere, then of course the coordination number at chromium would be lower, but of course still we would have isomerisms because the empirical formula would still be the same. So of course there are more conceivable hydrate isomers. So we could, for instance, also move the third aqua ligand from the first coordination sphere to the crystal, and the remaining chloro ligand here in the second coordination sphere to the first coordination sphere. But in this case, nature just doesn't do this, and this hydrate isomer is hypothetical. So here's just another example. So here we have tetraamine, aqua, chloro, cobalt, 2+ chloride. So there is a hydrate isomer to that, in which, again, an aqua ligand, in this case, the only aqua ligand that we have from the first coordination sphere to the crystal where it now exists as a hydrate. And like previously, we move one chloride, anion, from the second coordination sphere to the first coordination sphere. Okay, in this case, we have two hydrate isomers. Okay, then another important constitutional isomerism is the ionization isomerism. And please know all these terms. So you need to know what defines a hydrate isomerism and what defines an ionization isomerism. You have to also be able to name forms of constitutional isomerism. So please memorize these names. So in the case of an ionization isomerism, we swap up ions that are in the first and the second coordination sphere respectively. For instance, here we have pentaamine nitrate, cobalt 2+ sulfate, and you see that here you have a nitrate ligand in the first coordination sphere and a sulfate anion in the second coordination sphere. Now we can swap up the sulfate and the nitrate, okay, and that gives an ionization isomer in which now the sulfate binds directly to the cobalt and the nitrate is in the second coordination sphere. So this is called ionization isomerism. So the next form of constitutional isomerism is the coordination isomerism. So this form of isomerism requires that at least one isomer has two different metal ions. And the ligands are bound differently to the different metal ions. So here's an example of a first isomer. So in this case, we have diamine, dichloroplatinum. So we have two amine ligands and two chloro ligands bound directly to the platinum. We'd expect that this is a square planar complex. And there are two coordination isomers to that now have two metal ions, both. Okay. So they are both made of a complex cation and a complex anion. So here we have a complex cation in which three amine ligands and one chloro ligand are bound to platinum, and three chloro ligands and one amine ligand to the other platinum. So this is the complex cation here, and this is the complex anion here. And then we have a third coordination isomer in which we have four amine ligands bound to the platinum that makes the complex cation, and 4 chloroligands bound with the platinum that makes the complex anion. So at first, it may not be obvious that these 3 compounds are actually isomers to each other, but they actually are, and we can prove this by determining the empirical formula for all of them and show that the empirical formula for all of them is indeed exactly the same. So for this isomer here, we have 1 platinum and 2 amines and two chlorines. Okay, so the empirical formula would be PTN2H6Cl2. Now, what about this one? So here we have 2 platinums. We have overall, well, 4 amines, okay, and we have overall 4 chlorines. So now we see that we have twice as many platinums in comparison to here. We have twice as many amine ligands in comparison to here, and we have also twice as many chloroligands in comparison to here. So therefore, if we just divide the number of platinums, amines, and chloroligands by 2, well, we will get the exactly same empirical formula as for this one here. Okay, so now for this isomer here, we have also 2 platinums, as you can see here. We have also 4 amines, just like here. And we have also 4 chlorines, just like here. Okay, therefore the empirical formula for this compound and for that compound also needs to be exactly the same. And that proves that these 3 compounds are actually isomers relative to each other. All right. So now we can have different kinds of coordination isomerism. It can be that, for instance, the metals are different. So in the previous example, all the metals were platinum, but not necessarily the metal has to be only of one kind. It can be also of different kind. And an example for that is here. So here we have 2 isomers that are coordination isomers. And in this case, we have 3 ethylenediamine units bound to a cobalt, and that cobalt makes the complex cation. And there's actually a bracket missing here. And we have 6 cyanoligands that are bound to this chromium here, making the complex anion. Okay, so now we can swap up the cobalt and the chromium, and that gives then this coordination isomer here. So in this isomer, we have the ethylenediamine ligands bound to the chromium, making now the complex cation, and these 6 cyanoligands bound to the cobalt, now making the complex anion. So that's another possibility, and we can also have coordination isomerisms with metals in different oxidation states. So in this case here, both the chromium and the cobalt, were in the oxidation state +3. So here we have an example for coordination isomerism in which we have platinum in different oxidation states. So here we have a platinum 2, which is bound to 4 amine ligands, making a complex cation with a 2+ charge, which is then counterbalanced in charge by this complex anion here, in which platinum is in the oxidation state +4, and 6 chloroligands are bound to this platinum. So we can see that a -2- charge here results because the 6 chloroligands have a 1 negative charge, and the platinum is in the oxidation state +4, so 2 negative charges remain at the anion. So this here is the respective coordination isomer to this compound here. So in this case, you have the platinum 4 as part of the complex cation. So in this complex cation, we have now 2 chloroligands and 4 amine ligands. Okay, that again gives the complex cation with a 2+ charge because the platinum has a oxidation state of 4. The amine ligands are neutral, the chloroligands are anionic, and that reduces the 4+ charge to 2+ charge here at the complex cation. And then in this case, and again, I have a typo here, so this must be platinum 2. So in this case here, the platinum is bound to 4 chloroligands, but because it's platinum 2, we have here 2- negative charge compensating the 2+ positive charge here. So this actually is platinum 2 and not platinum 4. Please correct that on your slide, and I will also correct that. All right, so this was the constitutional isomerism. Now, the coordination isomerism. The next constitutional isomerism is the linkage isomerism, also called the ambidentate isomerism. And it is always observed when we have ligands that have more than one reactive end. And that gives these ligands the possibility to either use donor atom number 1 at one end or donor atom number 2 at the other end. So these isomers are often similar in energy, and therefore it depends a lot on the reaction environment which isomer will form. So for instance, the solvent can play an important role, and here's an example for this. So the thiocyanate can make linkage isomerism because it can either bind with the sulfur or with the nitrogen to a metal cation. In this example here, it is the palladium. So you see here that we have 2 thiocyanate ligands binding with the sulfur. In this case, this ligand is called the thiocyanate ligand, whereas in this isomer here, we have 2 thiocyanate anions binding with the nitrogen to the palladium. And in this case, the ligand is called the isothiocyanate ligand. So in polar solvents, this isomer here is preferred, whereas in apolar solvents, this isomer here is preferred. We could speculate why. One explanation would be that, well, in this isomer, we have the more electronegative element that can make hydrogen bonding with the solvent being the unreactive end, whereas here the more electronegative atom is bound directly to the platinum, and the sulfur can make less hydrogen bonding to polar solvent, and this may be the explanation as to why. In apolar solvents, this isomer here is preferred, whereas in polar solvents, this isomer here is preferred. So there are also other examples of ligands that can be ambidentate. But before we go to that, here's just another interesting example in which the thiocyanate ligand binds differently within the same molecule. So you see that in this molecule, we have this thiocyanate acting as an isothiocyanate ligand binding with a nitrogen, and another one which binds as thiocyanate ligand with a sulfur. So even this is possible, and we could ask, well, what could be the reason for this behavior? And that becomes clear when we look at the steric requirements. You see that there's one other ligand which is bound to the palladium, and it's very bulky here on this side, but it's actually not so bulky here on the other side. So because of the bulkiness, in this case, the sulfur binds, because in this case, the ligand can actually bend away from these bulky substituents, whereas in this case, there's far less bulkiness, and therefore the nitrogen is preferred to bind to the palladium. All right, now here, really now just a few, or one other example for an ambidentate ligand. So the nitrite anion is another example of a ligand that can do this. So the nitrite anion can either bind the nitrogen to the metal, in this case it's called the nitroisomer, or it's being bound with the oxygen to the metal. In this case it's called the nitritoisomers, and nitritoisomers are usually more stable. Okay, now this is all the constitutional isomerisms that I want to discuss. So now let's move over to the stereoisomerism. So as I said before, when we have stereoisomers, then the bonds are between the same atoms, but the ligands are at different coordination sites. So we know two basic forms of stereoisomerism, and you probably know that from organic chemistry. You know which are the two major kinds of stereoisomerisms.
Cis and trans?
No, that is a relatively specialized form. So there is the diasteromerism, and there is the enantiomerism. So these are the two main types. So what distinguishes these two? Well, when we have enantiomers, then the respective isomers are mirror images to themselves, okay, whereby these mirror images cannot be superimposed, otherwise they would be identical molecules. Whereas, well, diasteromerism is everything else, right? Which is not enantiomerism, so it just means that the two stereoisomers do not behave like mirror images to themselves, but are differently in other regards. Okay, so they are not mirror images with each other, but they are mirror images of each other. So enantiomerism always implies chirality. Okay, so enantiomers are always chiral molecules. Okay, remember what chirality means? Chirality means that no improper rotation reflection is present in the molecule, or in another view, we can only have the identity and proper rotations, but no other symmetry elements. Okay, whereas diastereomers are not necessarily bichiral, but they can be chiral. when they are chiral, then there must also be an enantiomer to that respective diastereomer. Okay. Okay. So let us illustrate this concept by one example to make it really clear. I'm taking this example here from the organic chemistry, but it applies exactly in the same way also for coordination chemistry. So, for instance, we know different stereoisomers of tartaric acid, for instance, L-tartaric acid, which is the natural form of tartaric acid that we find in the grapefruit. And you see here the Fischer projection of the L-tartaric acid. And in the Fischer projection, we have here these carboxylic acid groups at the end of the carbon chain. So overall we have 4 carbons here, these 2. And here there's another carbon not drawn. Here there's another one. And then in the L-tartaric acid, we have this OH group here pointing to the right, and this one here pointing to the left. So the Fischer projection relates to this absolute structure of tartaric acid. So if here the carboxylic acid groups, as well as these 2 carbon atoms in the plane. Okay. And now this OH group points out of the plane toward us. Remember here that these 2 carbon atoms are sp3 hybridized. Okay, so the hydrogen of this carbon atom would actually point to the back, but it's not drawn here. Whereas this OH group here points below the paper plane, and the respective hydrogen, not shown here, would point toward us. All right. So now, in addition to this isomer, we have the D-tartaric acid, and the Fischer projection is shown here. So now, the D-tartaric acid, this OH group here points to the left, and this OH group here points to the right. So now, which absolute structure does that correspond to? Well, it's this structure here. So this OH pointing to the left means that the OH group actually points into the paper plane. Okay, so this OH group points away from us, whereas this OH group, which points to the right, shown here again, points actually toward us. So now, these 2 isomers, they are enantiomer to each other. So they are mirror images to each other, and they cannot be superimposed. So now it's not immediately clear that these 2 are mirror images to each other, but it becomes actually clearer when we take this molecule and rotate it by 180 degrees around this carbon-carbon bond. Okay, now when we do this, then these carboxylic acid groups here, they point to the left, okay, not to the right anymore. So now this OH group, which formerly pointed into the paper plane, now here points out of the paper plane toward us, and this OH group here, which previously pointed out of the paper plane, will now point away from us. So now you can see that this form of the molecule, which is identical to this one, can be superimposed, it's the mirror image of this one. Okay, so we can draw a mirror plane in between these 2 molecules. Okay, and then through that mirror plane, this OH group would be mirrored into this position. This OH group would be mirrored into this position. This carboxylic acid group would be mirrored over here, and this carboxylic acid would be mirrored over here. And we would have proven that these 2 are mirror images to each other. Okay, so because of that, both of these molecules also must be chiral. So if we look for symmetry elements we would find only the identity in possibly proper rotations, but no improper rotation reflections. Okay, so in this case, we would actually only find that there's a C2 axis standing here. Okay, and we rotate around 180 degrees around that C2 axis. Our molecule would superimpose, but there are no other symmetry elements. So now there's a third form of tartaric acid, and this is called the mesotartaric acid. And you see the respective Fischer projection here, and in this Fischer projection, both OH groups now point to the right. And in the absolute structure, then this means that both OH groups, they point out of the paper plane toward us. Okay, so now at first glance, you may think, well, there's a mirror image to this as well. Okay, but before we go to that, we should realize that this mesotartaric acid is not a mirror image to any of these two that we previously considered, right? But certainly it's a stereoisomer, and for that reason, that mesotartaric acid is a diastereomer to both the D-tartaric acid and the L-tartaric acid. Okay, so now one may think that, well, there's a mirror image to this one, okay, which would be this one, where both OH groups now point to the left, and these two would be mirror images to each other, okay? Or these two here would be mirror images to each other, but these two are actually identical molecules because you can superimpose these two mirror images, right? And you can do this by rotating just by 180 degrees around this carbon-carbon bond. Yeah, and then these two will superimpose and these two will also superimpose, and that proves that they're actually identical or not two different isomers. Okay, then let us stop at this point here, and I will further expand on stereoisomers in the next class. Let us stop.